Newton's third law of motion. Before we start to learn about the third law of motion, let us revise what we learnt in the first two laws of motion. Newton's first law of motion, it stated that if we have a body and if this body is subjected to an unbalanced force, say F, there will be a change in motion of this object, which means if the body is at rest, it may start moving. If the body is moving, it would come to rest, or there would be a change in its velocity. So the first law of motion tells us an unbalanced force is required to change the motion of the object. Now Newton's second law now gives us the magnitude of this force, and it says F equal to m into a, means this force that produces a change in motion. Change in velocity means an acceleration. The force produces an acceleration, and the value of this force or the magnitude of this force can be found out by the expression F equal to m into a. And now for Newton's third law of motion tells us something very interesting. Suppose we have two objects, say A and B, and object A exerts a force on object B. We'll call this force as Fa. Now B also will exert an equal and opposite force on object A. We call this as force B. So if one object exerts a force on the second object also exerts an equal and opposite force on the first object. Now both these forces are equal in magnitude. Force A is equal in magnitude to force B. But however, their directions are opposite, like you can see in the figure. Force A is acting on B and the force B is acting on A. So for this we always put a negative sign because they are in opposite direction. The next question comes, will they cancel each other? Are they balanced forces? Because these forces are equal and opposite. Are they balanced? They are not balanced forces. To be balanced forces, they should be acting on the same body. Say I have a body C, and this force A is acting on C, and the force B is also acting on C. In this case, they become balanced forces. They are equal in magnitude, opposite in direction, and they act on the same body. So here the net force equal to 0, so we call them balanced forces. But in this example, here in Newton's third law, these are unbalanced forces. They may be equal in magnitude and opposite in direction, but they act on different bodies. And because they act on different bodies, they do not cancel each other. Force A acts on B and force B acts on A. So to go back to Newton's third law, that Newton's third law says that if an object exerts a force on another object, the second object will exert an equal and opposite force on the first object. So we go ahead and state the law, Newton's third law. To every action, there is an equal and opposite reaction. The launching of a rocket is a good example of Newton's third law. Remember, the Newton's third law said to every action, there is an equal and opposite reaction. Now in the rocket, a large amount of fuel is burnt, and this fuel is then pushed out or rushes out in the downward direction. So there is a downward force that is produced. To this downward force produced, there is an equal and opposite forward force that is exerted on the rocket. And this upward force then pushes or propels the rocket in the upward direction. So repeat it again. Here we have a downward force, and how is this downward force produced? By the gases that are burnt in the fuel tank and are expelled out in the downward direction. So this is the action. To this action, by Newton's third law, there will be a upward force produced, and this upward force, which now we call reaction, pushes the rocket in the upward direction. So the burning of gases and the gases that are pushed downwards produce the action, and to this action there is a forward or upward reaction that pushes the rocket up. We can demonstrate the working of a jet engine by using a balloon filled with compressed air. Here is a red balloon filled with air, and its mouth is untied. As soon as the mouth of the balloon is untied, you find the balloon begins to rise in the upward direction. When the air is released, it moves here in the downward direction. To this, there is an equal and opposite force acting in the upward direction, due to which the balloon begins to rise. Here is another example of Newton's third law. As this man jumps out from the boat into the deck, he exerts a backward force. To this backward force, there is an equal and opposite forward force that pushes the man ahead. But since the boat is floating and not fixed, the boat will push behind, will move a little distance behind. So that's the reason why if a man jumps out from boat, the boat moves backwards. I repeat again, in order to move forward, the man exerts a backward force, and that is action. To this action, there is an equal and opposite reaction which pushes the man ahead. But this action pushes the boat behind because the boat is floating and it's not fixed. Why does a gun recoil? Which means every time we shoot a bullet or fire a bullet out of a gun, the gun moves backwards. The reason is, in order to fire a bullet from a gun, the gun has to exert a forward force to push the bullet out. This force is action. According to Newton's third law, to this action there will be an equal and opposite reaction acting backwards. And this backward force, which is the reaction, will push the gun backwards. So every time a gun is fired, it recoils, it moves backwards. Newton's third law can be also used to explain the way we walk. When we walk forward, the foot exerts a force in the backward direction, and this is action. To this, the foot then gets a forward, equal and opposite forward force, and this is reaction. So next time you take a step, you try to find out in which direction your foot exerts a force, and you will notice you would be exerting a force in the backward direction in order to move forward. Here is yet another picture to demonstrate the way we walk. So this person, in order to walk in the forward direction, he is exerting a backward force with his legs and with his feet, and this hence he experiences a forward force. Why is it difficult to walk on ice? The reason is, when we walk on ice, because of less friction, we find it difficult to exert this backward force. We are unable to exert this backward force. Hence, we do not get a forward force. And it is very easy to slip on ice. In this picture, you can see that this man has worn shoes which creates greater friction, and because of this greater friction he can now exert a backward force, and to this backward force he'll get an equal and opposite forward force which will push him ahead. So why is it difficult to walk on ice? As there is no less friction, we find it difficult to exert a backward force, and hence we do not get a sufficient forward force to push us in front. When a fireman directs a powerful stream of water on a fire from a hose pipe, the hose pipe tends to go backwards. This too can be explained by Newton's third law. So here you can see a fireman who has to hold onto the hose pipe very tightly, and if he doesn't do so, the hose pipe would slip backwards. Now when the water is flowing through the hose pipe, there is a force in the forward direction, because the water is flowing up with great force. So this is the action. To this there will be an equal and opposite reaction in the backward direction, and this reaction in the backward direction will pull the hose pipe or push the hose pipe backwards. Hence a fireman has to make sure he holds on to the pipe very tightly. If not, it will fall behind. A swimmer pushes the water backwards in order to move forward. So here you can see when we swim, if we want to move forward, we push the water backwards. And when we push the water backwards, that is the action. To this we get an equal and opposite reaction that pushes us forward. So here is the action. To this there is an equal and opposite reaction that pushes our bodies forward. The next we'll see why a runner presses the ground with his feet before he starts to run. In this picture, here you see the runner pressing the ground in this direction, which is action. To that he gets an equal and opposite reaction that pushes himself forward. In the second picture too also, you see here this structure here, which are usually used for sprinters, and when the sprinter is about to take off, what he does, he exerts a strong force in the backward direction. To this he gets an equal and opposite force in the forward direction that pushes him ahead. So this was the action. He pushes his feet backwards. To that he gets an equal and opposite reaction in the forward direction. I'll just put this in another color. This is the reaction, and because of this reaction the sprinter is pushed ahead. This backward force is the action, because of which he gets a forward force that pushes his body ahead.